Hi everyone, this is Anjali Bhavan, and today I will be talking about getting started with vector representations of language. This video is brought to you by MLNerdie Delhi. So let's get started. Firstly, before we begin this talk, I'll give a brief about myself. I am currently working as a software engineer at Paytm, and I soon will be starting my MS in computational linguistics at the University of Washington. Before this, I have worked on many NLP research papers and projects. My research area has been quite varied, and I have worked on projects like machine translation, speech emotion recognition, and more recently, context-based hate speech detection. Okay, so what do we mean by word embeddings? In the most fundamental sense, word embeddings are nothing but numerical representations of words. Basically, these are words converted into some numbers which would be readable for a computer. Now, since computers now process literally everything on the planet, so why not words? Why this was kind of the logic behind representation of words in languages using in a computer using word embeddings. Now, these word embeddings are useful in a variety of situations like speech analysis, speech recognition, text analysis, voice technologies, assistants, etc. etc. Now, these word embeddings are usually based on some model, which helps a computer to study and generate these vectors and embeddings. We will be looking later on at what a statistical model of natural language means. Why do we need word vectors? Like, why can't we just feed words into a computer, and why can't it just understand? The the rationale the rationale behind We will be exploring now the rationale behind usage of word vectors. Basically, we wish to build a language model, that is a statistical probabilistic model which would represent language to a computer. Why this? Why not an integer representation? For instance, we could just give 1 to apple and 2 to ball and so on. Like, why can't we just discretely associate words? This was done actually. This was tried in much earlier systems, and of course it did not last for long. Now, why did it not last for long? What went wrong? Because this by logic, this seems pretty obvious, right? You're assigning particular numbers, and a computer can read numbers. Now, this is bad because in language, context matters. In language, meaning matters. Words are not isolated in language or a sentence. You cannot just put in random numbers or words in between to create sentence and meaning for even a computer to understand. For instance, if there's a movie review which says the most delightful thing about this movie was the popcorn, it that does not mean that the movie was delightful. This means that the movie was so bad that the only good thing about the movie was the popcorn, right? So even though this contains words like delightful, the sentence itself is not positive. Now, such integer representations cannot involve such context, and integer representations are also very easy to overflow, are very unstable and difficult to handle in the long run. The basically so this so in an integration of words did not work. Now, the next rationale was, what if we use vectors, a collection of numbers, instead of integers to represent words? Vectors are basically a list of numbers with a known length called dimensionality. So why not use that? This was next, and this was started by one hot representation. In a one hot representation, what happens is there's a vector of the size vocabulary, that is the number of words. Vocabulary size is the number of words in a vocabulary, and each word's vector is the size of that vocabulary. Now, each word is given its dimension. For example, you can see in this example, like apple is given the first category, chicken is the second, and broccoli is the third. So when they're one hot encoded, apple's vector will read 100, that is 1 for apple and 0 for others. Chicken's encoding will read 010, that is 1 for chicken and 0 for others. And broccoli's will read 001, 1 for broccoli and 0 for others. That is, value will be 1 in that dimension and 0 for all other words. And this way we can represent each word in a vocabulary. Now this made sense, right? This would not cause integer overflow, and this would not be as unstable as discrete representations. There are advantages surely. One of them was that every word was treated the same. Now for example, the number 8 is greater than number 1, but it is not more important than 1 just because it is greater. 8 and 1 would be treated the same in a one-hot representation. However, this approach also had limits. The limits like context and meaning, which were the same problems that integration presented as well. One-hot encoding again does not consider context and meaning. Like for instance, if there's a sentence called "I am dieting, I cannot eat dash," then dash should contain food items or junk food items. Like it should not contain "I can't eat football," right? It should contain words that make sense. Not all words have equal weightage. Not all words should have equal weightage, as one-hot representation associates. There is another disadvantage to one-hot representation, which is a more serious problem, which is the curse of dimensionality. What is the curse of dimensionality? It's a common problem with one-hot encoded vectors. And for instance, now what happens is, if we when we're analyzing real life documents in text and speech, vocabulary size can often go up to like hundreds and thousands and millions, because there is no limit to language, and you can have bunch together many languages as well. So the vocabulary size can commonly be taken to the order of 1,000,000. So if we have a 5-word sentence, and each word's vector is of the size of 1,000,000, which is the vocabulary size, then we are handling 5 vectors of size 1,000,000, which is of course absolutely unsustainable in the long run, consumes a lot of power and resources, and is generally not a good practice if one were to factor in efficiency and insightful analysis as well. This also leads to gigantic sparse vectors. As in, sparse vectors are those that contain a lot of zeros. This is the case here, right? We have almost 1,000,000 zeros and one in a huge vector. So sparse vectors are very difficult to work with. They consume a lot of resources, and thus the curse of dimensionality poses a problem which needs to be tackled. So what's the solution to this? Like, what do we do if even vectorizing in a simple manner is not working properly? The solution is a distributed representation of words. Now, if we are modeling words for a computer, if we are teaching a computer to understand words and a language, then it would be better if they also factored in context and word order. For instance, there are I am a girl. In this sentence, am must come after I. Am should not come before I, because that does not make sense in this sentence. Word order is important, as is context important. For if a sentence is talking about food, there should be food words in it. There should not be sports words. There should not be film words. There are some words which can be similar as well given the context. For example, I love eating dash. So here you could fill in words like apple or chicken, and they are similar food items. They are not like something as varied as a news piece or the president of America, right? So Modeling words could be improved by taking advantage of word order and context. The idea is to look at a full distribution of all the contexts of a word in a corpus. That is, what all situations a word is to be found in, all the situations should be gathered together and factored to generate that word's embedding. Now, how was this done? So, some initial approaches to this involve word clusters. Now, word clusters were first introduced by Brown et al. And clustering in generation of word clusters, a clustering algorithm organized words into clusters. And for instance, there was a food cluster, there was a sports cluster, there was a news cluster. This turned out to be quite useful, and it was and is still be used is still used in various contexts. Like you must have heard about Twitter and analysis of trends and patterns and speech. So many of those instances still use clustering algorithms for gathering together similar words and contexts. Another approach was frequency-based vectors. Now, in frequency-based vectors, each dimension corresponding to the corresponds to a frequency of the word type in some context. For that is, each vector dimension in the words vector corresponds to the context the word was found in. So basically, the vector contains all the contexts the word appeared in. Now, this representation gave rise to vector semantics. Semantics is meaning. So, like it was attempted to derive logical meaning out of vector representations. For example, a king and queen would be related in a similar manner as man and woman. So, is king minus queen equal to man minus woman? Like, do these mathematical representations make sense? Vector semantics studies that. However, a real transformation in the way we perceive and analyze vectors was brought by a 2003 paper by Joshua Bengio, who introduced neural probabilistic language models. He introduced a statistical model of language, which is given here. The idea was that given the context, given the past n words in n minus 1 words in a sentence, can we predict the next word? The probabilistic model Bengio presented attempted to answer this question. Now, the idea is to learn a good language representation based on this probability distribution. So in this case, models like n-gram models are useful. Now, n-gram models construct tables for every next nth word, taking the n-1 words as context. For instance, what can come after I like eating dash? So if it is I like and eating, what all words can come after that? Food words. So n-gram models will construct tables for every nth word. So after I, it should be love. After love, it should be eating. After eating, it should be something, some food. So this was a proposed method, and this is if in case you've studied probability before, this might seem like calculating the conditional probability of an event based on past events. Like given some past events, we are calculating the next event. We are calculating the probability of this word occurring given that these other words occurred before it. So, since this factors in context, this is a good way to go for constructing a language model. So, Bengio proposed that a machine learning model could be used to construct a good statistical language model with sequences of words as input. We give the machine learning system a sequence of words, several sentences, a large data set, and we teach it to model this probability distribution. we teach it to predict some words given their background and context. So basically a summary of the idea was to, with each word, associate a distributed word feature vector and express joint probability function of word sequences in terms of these feature vectors. That is, express the probability function in terms of these feature vectors and simultaneously learn vectors and parameters of this probability function. Since now the idea is here to learn, this can be automated. This can be done by machine learning. So this was what Bengio proposed. Now, what are n-gram models? N-gram models are Markov models. Now, what are Markov models? Markov models are conditional probability models. They help predict an event given given past events. Like if history is given, can you please come? Then the next word will be here or there. Like this probabilities are assigned to this using the statistical model described in the previous slide, and such models are used in numerous instances like speech recognition, computational biology to map sequences of DNA, and even computational linguistics, text analytics, social media analysis, and so on. We are trying to model this probability function. We are trying to learn the best parameters for this, so like the most logical words are predicted, so the most logical sentences are constructed, and for this we are using machine learning. We are optimizing this function. We are maximizing log likelihood of the training data so that we get an excellent language model. So like the computer can approximate learning a language. Now there are downsides to using n-gram models as well. The downside is that n-gram models do not model long-term dependencies, and as in they only consider a short context of size n-1 and do not factor in long-term dependencies. Basically, instead of a hard or soft partition in word sets to cluster similar ones, as was done in the clustering approach, here we are using a continuous learned distribution based feature vector for each word. So, but there are limitations to this as well, as in the lack of modeling of long-term dependencies. And it also another serious limitation of n-gram models is that these models do not consider linguistic factors. The prediction of words, the prediction of sentences, etc., is purely statistical, is purely based on a Markovian model, and it has got nothing to do with whether the word actually makes sense here. It is solely based on statistics and probability. Now we can get into exploring some well-known word embedding models. Some of the most famous ones which you must have heard are Word2Vec, which was developed by Dr. Tomas Mikolov at Google Research; GloVe, which was developed as an open source project by Stanford University; and FastText, developed by Facebook AI Research. The first model you will observe is Word2Vec. Word2Vec is an unsupervised algorithm for generating and using word representations. It was introduced by Mikolov et al. In 2014. Now, this method for generating embeddings uses either of two models, Cbar, that is continuous bag of words, and Skipgram. We will be looking in detail into both these models. Skipgram model. So a skipgram model attempts to predict words within the range of a given input. That is, the objective function is given here. Now you can see the probability here being, the log probability that is being predicted here is W the t plus jth word given the tth word. That is, the t plus 1th word is not being predicted. The t plus jth word is predicted. That is, within that is we are somewhat skipping some words in between. Skipping is a rough is to put it roughly, and we are instead predicting words at a certain distance, a certain range before and after the tth word. Now, what is the logic behind this? Like, why? Like, skipgram is basically using each current word as an input to a classifier, and it predicts words within a given range of size n. How its skipgram model uses negative sampling to differentiate between noisy and useful samples. Like, uh, what is negative sampling? So negative sampling is to is teaching is to teach the model to differentiate between what are the correct pairs of words predicted and what are the wrong pairs of words predicted. That is, a correct input output pair versus a wrong input output pair. So how does skipgram do this? So for each input output pair, the model samples k negative input random pairs from a unigram distribution. That is, for every true pair of input and output, for every correct word pairs, about k incorrect word pairs are sampled from a unigram distribution. Then a logistic regression model is used to differentiate between these two, and therefore it learns what is a correct pair and what is a wrong pair. In this, there is hope that some patterns are picked up, and these help in predicting words that, and it makes sense to the computer, and we achieve some degree of language understanding. The turns out skipgram is indeed a good model and with a reasonable approximation to language understanding. The authors noted in their paper that the vector skipgram vector of Germany plus the skipgram vector of capital is quite close to the skipgram vector of Berlin, which makes quite a lot of sense. This is a sensible high quality vector representation, and we can see that a non-obvious language understanding can be obtained using skipgram. Now, what does a Cbar model do? So Cbar stands for continuous bag of words. A Cbar model behaves like the opposite of a skipgram model. In a skipgram model, given a word, we predict the collection of predict words in a range around it. Whereas in Cbar, we are giving as input a range of words. We are giving as input the context. All of them are ranked the same. There is no order or specialty in them, and the output is then a word given all these contexts. The idea is to treat all history as the same. So it is a metaphorical bag of words from which whatever word you pull out, it has the same value. So every word in the input has the same value, and it is helped to predict the output word. Now we come to GloVe vectors, which stand for global vectors for word representation. Now there is a limitation of Word2Vec. That is, Word2Vec only considers local context window and not a global context window. For instance, if a document is about physics, and if a document is about physics and you see a chemistry word in it, if you see a biology word in it, Word2Vec looks at only the immediate sentence or immediate n-sized context. Word2Vec does not consider how many times that biology word appeared in the physics document, or in how many other contexts the word appears in. So GloVe aims to address those limitations as well by considering global co-occurrence statistics for word embeddings. As in, GloVe aims to consider local context but also global context by using co-occurrence statistics, like how many times these pairs of words are appearing together in a document. So embeddings generated by GloVe predict co-occurrence ratios. That is, if the embeddings of ice and water are pretty close, it shows that ice and water must have occurred together a lot of times in a particular text. For example, uh, let me take an example of ice and steam. So probability of ice being, since ice is a solid, the probability of ice and solid occurring together is high compared to the probability of solid and steam occurring, and so on. So like glow vectors consider consider these statistics, and this also makes sense because it's true that related words will occur together. Related, it's not very ubiquitous that unrelated words are occurring often together, or related words are occurring not occurring very far off or not at all together. So yeah, this is all I have from my side for this talk, and these are some of the papers I referred to while preparing this talk. I thank you all for your time, and I hope you learned something from this. Thank you.